What is up, AP Chemistry? Today we are going to be looking at intermolecular forces and intramolecular forces. It's the forces that hold things together, and we are going to learn that these bonds are going to affect the properties of the materials we're talking about. And I know I mentioned this before, but some crazy kid was like, "Hey, I think it's a good idea to glue my eyes shut with super glue." And, the poor kid, this guy right here, ended up going to the hospital. And yeah, the rest is history. But if he would have done this with a weak glue, such as Elmer's, it would have had a whole different effect. So it's the same thing when we're talking about intermolecular forces or intramolecular forces. If there are super strong bonds, it's going to affect its boiling point, its vapor pressure, its melting point. It's going to be soft depending upon the strength of the bonds, or hard. And so we're going to relate it to a couple things. So our goals are to learn how bonding affects BP, which is boiling point, VP, which is vapor pressure. So vapor pressure, it's been a while since we've studied this, but vapor pressure is the upward pressure that every single liquid exerts, as it's basically what's happening is it's evaporating, right? And it's the reason why we smell things. So, like, for example, perfume has a really high vapor pressure, gasoline, high vapor pressure. So we can smell it right away. And that's what we call the vapor pressure. So if the forces are really weak, it readily evaporates. And then melting point, same kind of concept. And we are going to relate this to KMT, which is just a fancy word for kinetic molecular theory, which says that everything's in constant random motion. Okay, so as you go through today, see if you can figure out what bonds hold what materials together and why. All right, so this gets us to our very first terms. So I just kind of want to talk about inter versus intra. So if you're on the interstate, if you're on Interstate 77, that goes all the way down to I think it's to Charleston, North Carolina, South Carolina, one of the Carolinas. And so inter means across, right? The internet is across nets. So intermolecular forces, this is the force across molecules. I'm not the best at writing on this. And so I'm going to draw it real quick. You guys sketch it out on your paper too. So here's a little molecule of water. And remember, water's polar, right? And along this side's positive. This is the hydrogen side. This side's negative. And along comes another water. And it's like, oh my gosh, there's a positive part. And so they are attracted to each other. And this attraction across molecules, that's where we get the word inter, right? Is an intermolecular force. And although these seem like they're pretty strong, and you've probably talked about hydrogen bonding in the past, and I know in bio and all that, they're nowhere near as strong as an intramolecular force. So an okay, so the word intra means within, okay? And what happens here is if I have something like Na bonded to Cl, this bond is actually super duper strong. It's not between molecules, it's actually between atoms. It is within the molecule itself. And since this is the case, this thing is super strong. One time I was after school, I was like, I'm going to try to melt some salt. So I got my torch out that gets up to like 2200 degrees Celsius, like 3000 degrees Fahrenheit, super hot. And so I started trying to melt it. I got red hot and the crucible blew up. Okay. So this bond, it still didn't melt. Okay. So that is a super strong. So we often say intermolecular force, these are really strong. And then intermolecular forces, these are relatively weak. Okay. And today, what we're going to do is we're going to look at where you can find these different forces and how we can understand them and all that kind of stuff. All right. So that's where we're at. Let's do this. Okay. So let's start about the three main basic types of intermolecular forces. I'm going to write this up top. These are inter. Okay. So all three of these are relatively weak. Okay. So for example, butter is held together by London dispersion forces. Acetone, dipole, dipole, and then hydrogen bonding, this would be water. All of these have relatively low melting points. They often will smell. I mean, think about like acetone smelling gasoline. Those are all different types of these types of forces. So, um, anyways, we're going to kind of distinguish between them. Here's the difference though. In intermolecular forces, these are all covalent molecules, all of them. So covalent means it's all nonmetals. Okay. And I almost said mentals. So it's all nonmetals. And they all exhibit like weak general forces, like weak melting points, weak, low boiling points, that kind of stuff, high vapor pressures. Okay, they all smell. Okay, so I'm going to kind of go through each one just to get you going on it. So let's first talk about dipole-dipole. Okay, so in dipole-dipole, I'll write this up top. I don't know why it got small up there. So dipole squared. Don't ever write it like that besides right now. So dipole-dipole, this is a force that's found within polar molecules. Now, the biggest lesson that I can get, and please write this out. So when in doubt, you're going to be like, go to moles. Well, yes, if it's a calculation or if it's an equilibrium problem, do an ice chart. But when in doubt, if it's a structure problem, draw it out. Like literally draw it out. Okay, literally draw it out. Find out, is it polar or is it not polar? And the only way to do that is to actually draw it out. So you're going to draw HCl out and you're going to find that, oh yeah, it looks like this. And this is definitely polar. This has a dipole like that. So this would be, the forces present in there would be dipole-dipole. Okay, if you draw out SH2SE, all right, you put it kind of looks like this. And you're going to find out, like I'm jumping ahead, assuming that you know how to do Lewis structures since we've done it for like 2 weeks, but who knows? Anyways, so this is definitely polar. So this is also has dipole-dipole forces. Now, the thing about these is these have what we call permanent dipole. Okay, so I'm going to talk about that. So permanent dipole, perm. So no matter how you do this, this is always going to be unequally distributed charge, which means it's always polar, which means that it always has dipole-dipole forces present. And so dipole-dipole is just, it's a medium force. It's actually the middle child. It's kind of in between everything, but it's not too weak, not too strong. It's kind of in between. And so that's how you can recognize dipole-dipole. If it's polar, all right, I'll write that one more time. So polar equals dipole-dipole, as long as it's not hydrogen bonding. All right, now let's go back. Ooh, so speaking of hydrogen bonding, so this happens to be the strongest of the intermolecular forces, but this is nowhere near as good as like, an intramolecular force like an ionic bond or metallic bond. So this is still relatively weak, but it's the strongest of the weak. All right. So I'm going to give you an analogy. It's not meant to be offensive, but let's just pretend you had to play baseball against like Nathan. All right. So Nathan's probably pretty good at baseball, whatever, or Serve was pitching for you. Right. So pretty good, that's not bad. But then let's say that Shohei Ohtani is pitching against you. Like that's way better. He's way better than Serve. Okay. It's no offense to him. He's just like a pro. So that's the difference between hydrogen bonding and like ionic bonding. All right. So this is your strongest bonding. And this is what gives water its like special properties. So water is actually unique in the world. It has like a super high boiling point, super high for its size, super high like freezing point. It makes life possible. But what makes hydrogen bonding special is it's like ultra polar. So it is. So I'm just going to draw a water molecule. So water molecules look like this, right? So it's bent, it's sp3 hybridized, it's polar all the way. And every year on the AP test, they make you, and I'm going to make you do this too. They make you draw. Can you believe them? Such jerks. They make you draw a hydrogen bond, and you're going to see this a million times between now and May. So this is a hydrogen bond right here. It's the negative side, right, is attracted to the positive side. And this hydrogen bond right here is relatively strong compared to, dipole-dipole. Now, there's a special category for it to be hydrogen bonding. It has to be lots of FON. Okay, and what I mean by that is it has to be H bonded with F, it has to be H bonded with O, it has to be N bonded with H. So H has to be bonded with F, O, or N. Now, why these guys? Well, it just has to do with electronegativity. These are the three top electronegativity, atoms on the table, electronegative atoms. And so what that means is they're the most like when they share, it's like, wow. So these electrons, they're sharing with F, and F's just like not nice. And so these electrons go way over. And so it becomes really, really polar. So hydrogen bonding is just like extreme polar is all. And You recognize it when you see F, O, or N. Now, it has to be bonded to H for it. So, for example, if you see something like this, like H, and then, you have, I'll just draw this out just because, why not? And there's a bunch of H's here, but the O is not connected to an H. It's not hydrogen bonded. This is dipole-dipole. It's polar. It's not symmetrical. Okay, so what you're going to have to do is you're going to have to look at something and tell the forces and tell its relative properties based off its forces. Okay, now this one's kind of weird. Now, you may have heard of this one before. This is the force found in nonpolar molecules. So it's called London dispersion in chemistry, or in bio, it's called van der Waals, which I just love the name van der Waals. So this is the attraction that's a result of like momentary unevenness of electrons to being distributed. So, for example, down here, as I'm talking about this guy right here, so there's a moment when the electrons are on the left side. So they're over here for a second. And since they're over there on the second, that side is like slightly negative. And then since another one comes by, it's like, oh, shoot, that side is slightly negative. So its electrons go to the other side because they want to be away from the other electrons. And this one becomes slightly positive. And this real slight attraction of momentary attraction is the only thing present in nonpolar molecules. Okay, so this is this force is present in nonpolar, but it's present actually in everything. So this blank is everything. Everything can have London dispersion forces, and everything does have it. And we call this like uneven distribution of electrons, this momentary lapse when they're on one side or the other. This is called polarizability. So polarizability is related to how many electrons you have and the tendency of them to, be on one side or the other. You don't really have to know much more than that. You have to know that polarizability increases with molar mass. And so what I mean by that is like CH4 is nonpolar, so it has London dispersion. And how do I know it's nonpolar? You draw it out. You find out that CH4 looks like this. It has four H's all the way around. It's all the same. It's perfectly symmetrical. It is nonpolar. Okay. And then if I were to compare that to C2H6, this is bigger, man. This one has more electrons. So therefore, it actually has more London dispersion forces. And since it has more electrons and more chances for them to be on one side or the other, it tends to have higher melting points. Okay. And in fact, if you follow all of them, like this guy is a gas, this is called an alkane, C8H 18. No, that would be H. Yeah, it'd be H18. This is octane, so that's gasoline. That's a liquid. So methane is a gas. Octane, these are all related to each other, all the same structure, all nonpolar. But if I go all the way up to C25H52, that's candle wax. That's a solid. So the reason why it goes from a gas to a liquid to a solid is because as they go bigger, the forces get stronger and you have more van der Waals forces. Okay, so this is the only thing found in nonpolar, but it's actually found in everything. So just be careful. Sometimes they try to trick you on this one, but not you, wily one. Okay, now, believe it or not, this unit, why did I save it towards the end? All right, so this unit that we're on, chapters 8, chapter 9, and a little bit of, I think this is a little bit of chapter 11, this is like 20% of your AP test. So this is like super important, right? So remember our three numbers are like 80% to get a 5, and that's pretty steady. Like you have to pretty much get there. 65 to get a 4, and then 45 to get a 3. 20% of your score of this comes from this kind of stuff. And there's a ton of this on there, and these are easy points. Okay? So keeping that in mind, I want to talk about intramolecular forces. Whoa. And then we're going to do this one. This might be a long video, but it's cool. It's good. I'm in the mode right now. I got approved to come back, so I am official. Got the letter and everything. Okay. So I just want to mention that there are four types of things that hold solids together. So molecular solids, these are all nonmetals. Okay. And what I mean by that is these are held together by what we call intermolecular forces. So these are held together by hydrogen bonding, by dipole-dipole forces, or by London dispersion / van der Waals forces. And then these three solid, and usually these, like, this is super weak. So molecular solids are like butter, Crisco, things that smell. They don't tend to be super hard. Sugar is a molecular solid. It melts really low. So that kind of stuff. Okay. And these guys, well, these ones, these are held together by intramolecular forces. So these are super duper strong. Okay, so like this is like diamonds are held together by covalent networks. And this is like salts. Okay, so where there's a cation and anion. And this would be just found in metals. Okay. So when we're talking about bonding, you're going to have to look at something and say, oh, that's hydrogen bonding, or oh, that's held together by covalent network, or it's ionic or metallic bonding. So I'm going to go through the different things. So there are some things that are what we call amorphous solids. So amorph, so without shape or form. So these ones are often known as supercooled liquids or different things like that, but you weren't going to mess with those too much. All right, so let's do this. Let's go through the different types. All right. So, first thing, ionic bonding is an intramolecular force. So, these things will form what we call a lattice, which we've already kind of talked about. So, lattices are like repeating things where there's a cation with an anion. Okay. And these lattices are like super, super strong. So, first off, they have high melting points and high boiling points. And again, just think salt doesn't easily melt. Now you can dissolve it, and all salts and ionic substances, they tend to dissolve in water because they're made of charged particles. So they do tend to dissolve. So ionic bonding is a metal with a nonmetal, something like Ki. So the properties of Ki has a high melting point. It does dissolve in water. It has a crystal structure that looks like this. It's made of cations and anions that are attracted, that kind of stuff. Okay, so when you see this, you're going to look at something, and if you see that it has a cation, a metal, with a non-metal, then you know that it is held together by ionic bonding, and it would actually, like Ki has a higher melting point than water. Water, even though it has hydrogen bonding, it doesn't compare to these intramolecular forces, and those three are ionic covalent network and then metallic bonding. All right, so anyways, that's the first type. So you recognize it by metal, non-metal. It has some unique properties. It actually conducts electricity when liquefied. So if you can liquefy an ionic salt, it will conduct electricity because it's made of ions. That's how you can do electrolysis. But it also dissolves, okay? And it's made of cations and anions and that kind of stuff. Forms a lattice. All right. Now, covalent network, these are things found in, like, there's pretty much three things that you need to know. There might be a few more that you'll run into, but if you see covalent network is like the max bonding. So this is a super rare type. It's found in graphites, which, believe it or not, graphite is carbon. It's like similar to diamonds. It's an allotrope. Diamonds, hardest thing out there, and sand, which also sand's really high up there. So these three things are where you pretty much need to know covalent network. Now, covalent network does nothing. It has a really high melting point, probably the highest. This and metallic bonding, some of the strongest bonding. Um, the actual bond is actually between atoms, and they form like a super strong lattice where it's nearly unbreakable for a lot of things. They don't dissolve, so they will never ever dissolve. So sand doesn't dissolve. Diamonds, if you have a diamond, you're not worried about taking it in the shower. Um, yeah, super cool, right? And so when you see sand, graphite, diamonds, you know that it's covalent network and that its properties are super strong and super hard, super awesome. Okay, now metallic bonding. Now I want to talk about this for a second. So this is this is just if it's a metal. Okay, so it could be a metal, it could be an alloy. And what happens with this is, first of all, this is intramolecular force. So metals, almost all the metals are solids. And the reason why they're solids is because the bonds are so strong. Now, what's unique about this is they have delocalized electrons. And I want to mention what that means. So when you have delocalized electrons, basically the d sublevels kind of all overlap in these atoms. Do you remember how a lot of these have like empty d sublevels and all that? And what that allows is that allows electrons to freely flow between atoms. And so all metals are conductors because of the type of bonding they have. So that is delocalized electrons are able to move throughout and be shared throughout the whole thing. They don't dissolve in water. So metallic bonding, just like covalent network, you're not going to find like iron dissolving in water. Well, they do rust and stuff, but that's a different, that's a chemical change, not a physical change. And it's super strong as well. So this is on the same order as like there are metals that have melting points in the 3,000, 4,000 degree range. They're super, super strong. Okay. Now, a molecular solid, these are two nonmetals held together by intermolecular forces, and they will be either hydrogen bonded, London dispersion, or dipole-dipole. And what you have to do is you first need to go through, and the rule of thumb is when in doubt, draw it out, right? So what we're going to do is you're going to pause and you're going to get a worksheet from your teacher that looks like this. Okay. And all you have to do is like, this is from ChemiBear, which is a great resource. It has like so many cool things you can kind of practice on. But this is like a skill that every chemist needs to know. So when you're doing this, first and foremost, what you need to do is you need to look at what they're giving you. So let me get this going here. So I'm going to do NH3 first of all. And you kind of need to like go through and rule stuff out. Okay. So I'm going to start with the covalent network here. So there's three things you're looking for. You're looking for sand, SiO2, diamonds, graphite, maybe some other weird like metalloid, but for the most part, I won't ever put like diamond, sand, graphite. Those are the three that I'm going to do. So this ammonia is not this. So we're not going to, it's no. Okay. So nope. I'm just going to kind of go through it real quick with you. Ionic bonding. Okay, so is NH3 a metal with a nonmetal? Because remember, the ionic bonding is always metal, and no, the N is a nonmetal, and it's not a metal at all. So we can rule out these three. So ammonia is none of those. Okay, so then I'm going to start with London dispersion forces. Is it nonpolar? So when in doubt, we draw it out. So you're going to do NH3, and when you draw these out, remember you're counting valence. You're doing what you've done over and over again, but eventually you're going to find out like they have a look, right? And certain things always look the same, and ammonia looks like that. It's real popular. So you can jump ahead if you know how to do it. But anyways, this is not polar. So it's not London dispersion. This is polar. Sorry. So this is not London dispersion forces. So it's either dipole-dipole or hydrogen bonding. And the way you tell, so it is polar, but the question is it hydrogen bonding is so much fun. It's so much fun it hurts. So what we mean by that is it has N attached to an H. So this is totally hydrogen bonding. Okay, let's look at the next one. So I'm going to clear this out so it's less messy. So krypton. Okay, so you're going to look at krypton. All right. And when we look at krypton, we find out that krypton is not metallic. It's not an ionic. I mean, it's just a noble gas. It's not network solid. It's usually not that. And so is it hydrogen bonding? Well, it's no fun at all. And it's not even polar. So it's London dispersion forces. And in fact, all the noble gases are held together by London dispersion forces because they don't bond with anything. They're just all nonpolar. So that's why they're all gases. Okay, let's try HCl. So when we look at HCl, it's not a covalent network. No. It's not ionic bonding because it has to be a metal with a nonmetal. Remember that. It's not metallic. Okay, it could be hydrogen because it has hydrogen in it. So we're going to come back to that one. So is it polar or nonpolar? So first of all, we look at it, it looks like this. So it's definitely polar because polar means it's like asymmetrical. So it is not that. No, it's dipole-dipole because it's no fun, no FON, and it's polar. All right, you getting the gist of this? We're going to do a couple more just to make sure. Okay, so F2. All right, let's go through it. We're going to start with covalent network. Is it diamonds? No. Is it ionic? No, it has to be metal, non-metal. Is F2 a metal? No. Is it so much fun? Now you got to be careful. Just because it has F in it, the F has to be bonded to an H, so it's no fun at all. So it's either London or dipole-dipole. So when in doubt, we draw it out, and it's like perfectly symmetrical. So it is totally London dispersion forces. It's not dipole-dipole. You're going through, and you are figuring out what is what. All right, let's take a look at this one. The next one's a little different. I'm going to let you do your thing. Okay, so KMNO4. All right, so first let's start. Is it a diamond? No. Okay, so it's not that. Is it ionic? Well, it's a metal with a polyatomic ion, so yeah, it is. Okay, do you remember we had to learn all these? It's sodium, or I'm sorry, potassium permanganate. So yeah, it's totally ionic. So there you go. It's over. I'm done. What about NaCl? It's ionic. Good. We did it. Okay, now I want to mention this one. Okay, SO2, because this one's tricky. All right, we're going to do this one. So first off, you go through and it's not covalent network, it's not ionic, it's not metallic, it's none of those. So now it's do you see how it's all nonmetals, it's SO2. And it's no fond because there's no O and H. So now the question is SO2, is it London dispersion forces or dipole dipole? And so the only way to do this is when in doubt, you draw it out. And when you draw it out, you have to know how to draw it out right. So it's gonna end up looking like this. I know what its structure is because I've done it like 1 million times, but it's actually has a resonance structure. And it looks like this. It's actually bent. And anything that's bent is always polar. So this is dipole dipole. But if you look at the next one, CO2, and I know some of you have run into CO2 a couple times, it's got a double bond. So this should be a double bond. I stink. Okay. And this would be London dispersion. All right. So here's what you're going to try. All right. You are going to go through and just like make sure you're all good on these. You're going to work your way through. And then you're going to check all your answers with a key. Okay, now there's a couple weird ones. So, like, this is a weird one. This is actually 16 is a weird one. But overall, you should be able to check it. I'll let you see the key after you're finished. Okay, so you're going to try to figure out. Remember, when in doubt, draw it out. And you should be super good on this one. This is super important. But that's pretty much what you need to know. Oh, I have memes. Before we stop recording, let's go to memes. I forgot I did. You can stop it if you're sick of hearing it, but I got memes. If I can get this thing off. This is just describing them, the properties of them. This is pretty important. Like molecular solids tends to be soft, low to moderate high melting points. Yeah, read that. It's pretty important. All right, and this is like, all right, which is the highest melting point? So look, London dispersion forces for H2. Oh shoot. Dipole, dipole, and water has hydrogen bonding. So that would have the highest melting point. Okay, but no one cares. You want the memes. All right, so let's do this. Okay. I'm going to narrate them just for good old time's sake. All right, see if this makes sense. So no bond, dispersion forces, dipole, dipole, and then hydrogen bonding. That's only for intermolecular forces, though. Okay, so good. So London dispersion force is weak, dipole dipole strong, or you could even put hydrogen bonding, which is even stronger. All right, so here we go. We have molecules, and then they think they're all good because they're intermolecular forces, right? But then intramolecular forces are so much bigger, stronger. It's just Star Wars. May the intermolecular force be with you. It's cute, whatever. Can't go wrong with that. Ah, the dark side of intermolecular forces and intramolecular forces await you in chem class. It's true. I just like raccoons. Okay, I'm going to be honest. So helium is nonpolar. If you have two helium, first of all, what's going on with that raccoon? But two helium atoms, this force between them is going to be super duper weak here. So that's a van der Waals bond. So cool. And then finally, learning both permanent dipole interactions and London dispersion forces, but knowing van der Waals, and they accept van der Waals on the AP test. So there you go. All right, I'm so excited to be coming back soon. If you're lost, you can always read the book. You've got this, people. There's people in class that know what they're doing. We've got this. Let's go. All right, I'm stopping this.